What's up, everybody? Hope everyone's doing all right. Had a good weekend. This is Mr. Chun with lesson 10.2.1. I mentioned to you all that uh, this might have been a while ago, but we're actually going to be shifting away from circles and we're going to go towards probability. And after this week is done and we go into next week, we're going to actually introduce a different kind of math, which is called combinatorics. Working with numbers a little bit more. And so, again, we're stepping away from our usual geometry and we're going to go a little bit more into probability. And so, with 10.2.1, we're first starting off with this idea of called conditional probability and independence. So, if we look at the introduction, it says when two events can occur either simultaneously or one after the other, how can you calculate the probability of one of them when you know the other has already happened? You will investigate this question today. Then, you will see how finding conditional probabilities will help you determine if two events are independent of each other. So, there's going to be a lot of vocab as we go throughout this lesson, and that will sort of guide us into observing different observations of our probabilities. So, to start off here, we got 10-61, ate the hard way. So Maribel is playing a board game, ate the hard way, with her friends. Each player rolls two dice in their turn and moves according to the sum of the dice. Sort of like how if you guys play Monopoly, you have two dice, anywhere from 2 to 12. However, if a player rolls two fours, called ate the hard way, they instantly win the round of play and a new round is started. Shayna stepped in the kitchen to get snacks when she heard Maribel shout, "Woohoo! I got an 8." Shayna knows Maribel got an 8. With your team, help Shayna investigate the probability that Maribel rolled two fours and won the round of play. In other words, we're calculating the conditional probability that Maribel rolled two fours, given that you know she already rolled a sum of 8. So we've seen the word given when we were in chapter 4 in first semester. And this is a specific condition that you need to have to then find the actual probability that she rolled two fours. So to start us off, this is going to be a nice little review from last semester. So for this one, it says to make a table to represent all the possible sums of numbers when rolling two dice. So there's a lot to this. So I do want to make sure that we include every single possible solution when we're going through this question here. And so the way that you can sort of do this, you don't have to make like a crazy table. You can just do, I'm just going to make a table for us. I think it just makes it easier. It might be a little hard to see since the letters are in the way here, but basically what we're doing is we're going to, on the outside here, so we got, let me see here, we got this, 3, 4, 5, and 6. And then 1, 2, 3, 4, 5, and 6. So there's going to be 6 by 6 table, and each side is going to represent all the possible options when in one single die. So the numbers 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I'd like you to make this table when you're doing this, and just basically, I mean, when you roll two dice, what do they add to? So 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, and lastly, 7, 8, 9, 10, 11, 12. So we got that going for us so far. So that's our table. Then part B, it says, however, since you know that Maribel rolled a sum of 8, the sample space has changed. So the sample space is only all the ways a sum of 8 can be rolled. So in our table here, you can shade or circle all the ways a sum of 8 can be rolled. So basically I'm asking, how many different ways can a sum of 8 be rolled? Or how many outcomes are in the new sample space? So wherever you see the number 8, it changes our sample space. So instead of all 36 total solutions, we're actually only working with 5. because these are the only numbers that you can roll an 8 with. So, specifically for part C, you're interested in the event 8 the hard way. How many different ways can 2 4s be rolled? Well, if we look at this die for the first die here and the second die, well, we only have one possible way to do it. So first die is up here. Second die is on the left. So if we take a look again, there's only one way to do it. One has to be 4, the other has to be 4. So really, to answer that question, there's only one way for part C. And we said that there are 5 outcomes for part B. So now, part D, what is the probability of the event 8 the hard way given, the keyword is given here, that you know Maribel already rolled a sum of 8s. So we're not doing it out of the total 36 outcomes. We're reducing our sample space to only 5 outcomes. So the denominator of our probability for D is 5, and of those 5, there's only one way to get 8 the hard way. So that's how this ends up working. Now, part E is a completely separate question from 8 the hard way. Becca rolls high, meaning she rolled a sum of 9 or more. So what is the conditional probability that she rolled an odd number, given that you know she rolled high? So I'm going to change colors here to sort of differentiate. We'll do green. So every single number that is 9 or higher, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So there's 10 total outcomes. Of the total outcomes, what's an odd number here? Well, we have 9, 9, 9, 9, 11, 11. So our probability to roll high is 6 out of 10, which if you can reduce it, please do. That ends up being 3 over 5. So that's what's going on with that question in particular. Unfortunately, I can't keep it, so I do have to erase it. So if you guys need to rewind, this is the perfect time to do it, as with any of these videos. But I do need to erase it to move on. And so we're basically, with our conditional probability, we're going to shorten our workload here. We're not going to have this crazy expansive space that we used to have in chapter 4. If we look here down here at 10-XC2, we're changing up sort of how we're going to do this. So at Einstein Technical University, ETU, data on engineering majors was collected. So it says in this table that there are engineering majors and other majors. And then there are also people that live off campus and live on campus. So if you think about U of I campus, as our best example, people that live on campus are literally in the university. So whether they're in a dorm, whether they're in an apartment within the university, that's what's on campus. And then living off campus is, if you think about the rest of Champaign or rest of Urbana outside of campus, you guys know what's off campus, what's on campus. So first of all, this is a very general question. What is the probability of a student living on campus at ETU? In order to answer this question, you need to figure out how many students there are. So the way that we sort of fill out this table here is we can count how many do we have of each category. Because at the end of the day, everything's going to add up to get the same number. So if I were to add across here, and I have this 30 and 170, add those together, we get 200. Then we add the people that live on campus. We have 6 and 34, which is 40. So if we add 240 together on the bottom right of the table, we can do 240. Now, how do we know this for sure? Well, let's go down the columns now. Engineering majors, there's 36 of them because 30 plus 6 is 36. Other majors over here is 170 plus 34, which is going to be 204. And so when you add these two together, they also add to 240. So that means there are a total of 240 students at ETU. So of the 240, how many live on campus? Well, if we take a look at this number here, this row represents how many total people that live on campus, whether they're engineering or non-engineering. So I'm going to write the probability 40 over 240, which again, please reduce if you can. 40 goes over to 240 6 times. So probability for part A is 1 over 6. Okay. So then part B, we're going to shade the cells with engineering majors. So go ahead and copy that table on your paper. and then we're just going to briefly shade it. And then I don't want to like completely shade it because I still want to see the numbers. What is the conditional probability of a student living on campus given, again, the word given, that you know a student is an engineering major? So we're changing the sample space. It's not out of 240 anymore. It's out of 36. There's 36 total engineering majors. So of that, how many live on campus? Well, we have this 6 here. 6 people live on campus out of the total 36 engineering majors. So we have 6 over 36 for part B. But again, we can reduce it, and it ends up being 1 over 6. Okay. So then part C, 2 events, A and B, are independent if knowing that B occurred does not change the probability of event A occurring. That is, 2 events A and B are independent if the probability of A given B is the same as the probability of A. So when I talk about probability of A versus probability of B, anytime the letter capital A is represented, it's like the first event probability. And then probability B, well, simply it's the second event probability. So whatever is mentioned to you first, that's your A. Whatever is mentioned second is your B. So when I read the rest of the question in part C, it says, are the events live on campus and engineering independent? So live on campus is the first thing that's mentioned. So that's A. Engineering is the second thing that's mentioned. So that's event B. So I need to figure out, does probability of A given B the same as probability of A? So probability of A is living on campus just in general. And we said that for part A, that was a 1 out of 6. So probability of A in this case is 1 over 6. Then probability of A given B, this is given that they are engineering. Given B, given that they are engineering majors. So of the 36, we said there was 6. And once again, probability of A given B, we already found that in part B is also 1 over 6 when we reduce it. So 1 over 6 equals 1 over 6. That checks out. So this means these two events, A and B, are independent. That's our answer for part C there. Okay, so independent again. If these two probabilities are equal to each other, that means they are independent. This is very important to know for this homework and the rest of this lesson, rest of this chapter. Now, part D. 2 events are mutually exclusive or disjoint if they cannot both occur at the same time. That is, 2 events are mutually exclusive if the probability of A and B is equal to 0. This means it's the intersection. So you got to look at the specific part of the table where A and B match. So this means, are the events on campus and engineering mutually exclusive? So if we take a look at our table, I'm going to erase some stuff here, clear it up. So living on campus and engineering, that means this is the 6 here. 6 out of the total 240. Well, is that 0? I don't think so. 6 out of 240 definitely does not equal 0. So how I would answer this is that on campus and engineering are not mutually exclusive. Or you can say not disjoint. They both achieve the same thing. So these are 2 important vocab terms that you do need to know. Independence, mutually exclusive, or disjoint. Okay. Just as a reminder as well, if things are not independent, the opposite of independent is dependent. I'm writing that in the middle here. Opposite of independent is dependent, which means the one event does depend on the other. Okay. All right, going to be erasing things. So if we go to 10-63, 10-64, we got some different tables here. So Mr. Rexinger is playing a game with his students. He randomly chooses a student from his class roster. If the player guesses the gender of the student correctly, the player gets an early lunch pass. Madeline is the next player. Which gender should she guess to have the greatest chances of winning the lunch pass? So, if we take a look, the first thing that we should do, just like I did for the previous problem, is add out the rows here. So we got 7 plus 7 is 14. Female is 5 plus 13, so that's 18 out of a total of 32 students. So total 32 students. So if she's randomly choosing the next player and it's guessing the gender of the student correctly, the player gets an early lunch pass. So out of the total 32, right? How many should she pick? Or who should she pick from, the male or the female here? Well, in this case, male is 14 out of 32. Female is 18 out of 32. So basically, which one has the higher probability class? Well, I don't know about you, but I think 18 out of 32 is bigger than 14 out of 32. So female is the way to go here because it's a bigger probability. So then, part B, Mr. Rexinger tells Madeline that the student is wearing jeans. Should Madeline change her guess? Well, probability of a female given jeans wearing jeans is not as it changes because now there's a total of 12 students wearing jeans because 7 plus 5 is 12. So if we know that the student is wearing jeans, this should change your answer because now it's not out of 32 anymore, it's out of 12, and it specifically comes from this column here. In this case, for part B, she should change her guess. Why? Because male has 7 out of 12, female is 5 out of 12. 7 out of 12 is bigger. So you want to go with the male then, if you know that the student has jeans. So we talk about independence. And so this word association is also very similar to it. So I'm going to read the second line here. Associations between variables are determined by independence. If two variables are independent, then they are not associated. If you think about it realistically, right? You associate with your family because you're family, brothers and sisters, mother, father, guardian, grandparents, aunts, uncles, cousins, etc. You are associated with them. So in a sense, you're dependent on one another. But if you're independent, like if I'm talking about myself and your sibling, I don't know who the sibling is. I don't know. I've never had them as a student. I'm not associated with them. I'm associated with you as my student, but I'm not associated with them because I don't know who they are. So that means that if two things are independent, that means they're not associated. It sort of makes sense. And on the flip side, if I were to write out another text here, if two variables are dependent, then they are associated. If two variables are dependent, that they are associated. So that's how things sort of flip-flop back and forth here. So then it's asking, are the events female and wearing jeans associated for the students in Mr. Rexinger's class today? So independence, what we talked about in 10-62, is the probability of A given B is that the same as probability of A. A in this case is being female, B is wearing jeans. So the probability of being female in this class is 18 out of 32. But then the probability of being female given the genes is 5 out of 12, which was our answer, technically our answer for being female here. So does 5 out of 12 equal 18 out of 32? Well, if you plug that into your calculator, you do 5 divided by 12, you get 0.41 or 42 if you round. And then 18 divided by 32, if you do that, you get 0.5625. Are these two equal to each other? No. So because of that, that means they are not independent, which means they are associated. So because the decimals the probabilities don't exist, not exist, because they don't equal, these events are associated because they are not independent. And then lastly, are the events female and wearing jeans mutually exclusive? So then from problem dash 52, probability of A and B has to equal 0. So if you take a look at female and wearing jeans, that equals 5 out of a total 32. So no, it's not. Nope. 5 out of 32 it does not equal 0. All right. And then lastly, we have 10-64. At Digital Technical Institute, the following data was collected. We have all these tables here. This time, we're first figuring out, are they associated? So does living on campus have the same probability as living on campus given that you're engineering? So probability of A given B equals probability of A. Well, if we take a look at everything and add it together, we got 200 off campus, we got 40 on campus. So our total students is 240. There's a total of 30 engineering and 210 other. So the first thing is living on campus. There are a total of 40 people that live on campus out of a total of 240. So our fraction here, or our probability, is going to be 40 over 240 on the right side. And then on the left side, it's given that you're an engineering major, do you live on campus? In this case, it's 0 out of 30, which is just 0. So 0 definitely does not equal 40 out of 240, or 1 over 6. So because of that, they are not independent, which means yes, they are associated. So on the right side here, I'm going to write 0 does not equal 1 over 6. So they are associated. Part B now, this is important. Are the events living on campus and engineering mutually exclusive? Are they mutually exclusive? Yes. Why? Because that's the probability of A and B equaling 0. So living on campus and being engineering, that's where the 0 comes in. So yes, 0 equals 0. That's good. So because of that, there are no outcomes. Because the intersection is 0. So that's how these tables work. And we're going to learn on the next lesson that these are what we call two-way tables. These are two different variables being compared with each other, and we're using these tables to organize our data. So I hope this helps. If you have any questions, again, feel free to email me. Hope to see you soon. Take care. Bye-bye.